Hi everyone, I'm Gabriel Nogueira from University of Campinas, and together with Tulio Richard and our advisor William Wolf, I will show our work about statistics of turbulent flows computed by large eddy simulations of a NACA0012 airfoil. Studies related to turbulent flows in airfoils find great applications in designing optimizations of aircraft wings, industrial rotors, and wind turbines for energy production. More recently, airfoil flows have been studied for the design of micro-air vehicles, where there is an interest in mimicking both the flight and performance of birds and insects. Besides that, the decrease of available area for airports and military bases will also bring the necessity of aircraft with vertical takeoff and landing, VTOL, like the Boeing V-22, showing the images on the left. All these applications have a common interest: drag noise reduction, increased lift, autonomy, and energy efficiency. This way, an initial setup was previously studied by Wolf in 2011 about autonomous noise in specific configuration. The results were compared against experiments performed by Brooks in 1989, and the sound pressure level revealed the tonal noise in the wave number around 9. In order to investigate the effects of Reynolds number, the tonal noise, and current structures based on the previous work, the simulations were performed for a smaller Reynolds number, 200,000, and a higher Reynolds number, 800,000, both with 5 degrees of angle of attack and Mach number 0.150. Below, the meshes are shown every 8 points. In the numerical methodology, the simulations are based on staggered grid, and for spatial differentiation, interpolation, and filtering, we use a 60-order compact finish difference schemes. For time marching, we use a 30-order Runge-Kutta and modified beam-warmer method. Spawns and characteristic boundary conditions are applied on the far field. Overset grids with a 4th-order current emitter interpolation between grid blocks. Periodic boundary conditions on span, and finally, random tripping in space and time in order to disturb the boundary layer on the section side. This video shows the specific configuration of the airfoil in the simulation. Isosurfaces of key criterion are present colorized by streamwise velocity. Noted that two-dimensional structures are formed after the trailing edge on the wake, and, as will be discussed later, are related to the tonal noise. It's possible to see the different characteristics of the turbulent structures along the boundary layer. While packs of hairpin structures appear more organized upstream, more elongated and disorganized structures are visible downstream. The simulations are shown in detail, and in the 200K simulation, it's possible to notice the transition and behavior of the structures along their airfoil, as well as in the 800K simulation, where the concentration of packets of hairpins are more evident, mainly near of the trailing edge. For mesh resolution, the grid refinement is applied along the upper region of the whole grid block. An assessment of grid resolution is provided in terms of wall units. The distribution of delta X plus, delta Y plus, and delta Z plus are shown along the airfoil surface, and one can see that the present simulations follow the best practice in terms of the wall resolve LES. Here, on left, we have the distribution of negative pressure coefficient along the airfoil surface. As can be observed from this figure, results obtained for Reynolds number are similar. On right is shown the surface distribution of friction coefficient. Friction drag is higher for the Reynolds 800K, and transition also occurs earlier for this case. This is a consequence for the upstream trip location, but the same observation could be made without the tripping. Turbulence statistics for both simulations will be present at 90% of the short of the airfoil, ensuring that the flow is developed. The mean velocity and Reynolds stress profiles are shown normalized by friction velocity. In the mean velocity plot, the viscous sublayer and log layer profiles are also present. Although the viscous sublayers are well matched by the simulation, it is possible to see a shift in the logarithmic regions. The effects of a universal pressure gradient, as well as the curvature of the airfoil, may cause this shift in the velocity profiles. As expected, the higher Reynolds number case shows a wider logarithmic regions than the lower Reynolds cases, and slope in the slope is similar to that given by the von Karman constant. The Reynolds stress profiles show a good comparison up to Y plus 100, since they are scaled by the friction velocity, which is an inner scale quantity. To the same position of charge airfoil and Y plus equals to 10, The mechanism of ejection and sweep through the scatter plots are shown. As can be seen in the animation on the left, when a negative tangential velocity fluctuation and a positive normal velocity fluctuation occur from the bottom layers, the fluid is pumped upward. This event is named second quadrant or Q2 event or ejections, whereas on the right, when a positive tangential velocity fluctuation and a negative normal velocity fluctuation occur from the top layers, the fluid is pumped downward. This event is named fourth quadrant or Q4 events or sweeps. Ejections and sweeps are evident in scatter plots with the direction of confidence ellipses for 90, 95, and 99% of velocity fluctuation. When we have the velocity components with the W velocity fluctuation, the same mechanisms don't occur, since the direction along the span is homogeneous. The same physical mechanism of ejections and sweeps is also evident when computing probability density functions. For the tangential velocity, we note the change in the positive skewness associated with the ejections to a negative skewness associated with the sweeps along the boundary layer. This mechanism also occurs for the normal velocity. However, it is more subtle for skewness. On the other hand, kurtosis will change with Y+, approaching to a Gaussian distribution. Among the several model decomposition techniques, we use the proper orthogonal decomposition, POD, to identify covariant structures in the turbulent flow. In POD, the vector of flow quantity Q is assumed to be a function of space and time, and it can be decomposed as a sum of time average flow, Q bar, and its fluctuation quantities. The fluctuation can be expanded in a combination of spatial modes and temporal dynamics. The snapshots of Q are computed at time, and in this way, the covariance metric C is defined as the product of a number of snapshots computed along a subdomain of the flow region. For the calculation of the covariance matrix, we also define a vector beta that determines which norm is being used in the POD analysis. So, in order to identify covariant structures, we investigated U norm, turbulent kinetic energy norm, and V norm. The POD is divided into two domains, the wake and the boundary layer on suction side between 40 and 95% of the short airfoil, in order to identify the covariant structures. Below are shown the normalized eigenvalues for each flow region, not mainly the pairing in the first more energetic modes. For POD on wake, the first special modes for both ranges are shown on the left. It's possible to observe two-dimensional structures with great energy on the wake after trailing edge. These structures are responsible for tonal noise, especially when on the right, one looks at the Fourier transform of the first mode, and which is associated to the tonal peak of 7.35 for the Reynolds 200K and 11 for the Reynolds 800K. In addition, these structures in peak are highlighted with the use of 25% of a Gaussian filter, as will be shown next. When look at the Fourier transform maps, the impact of a filter with the removal of noise in each POD mode is evident. Using 25 of Gaussian filter, it is possible to notice that the amplitude and wave numbers associated with each mode is evidenced with greater clarity without, however, filtering the structures too much. Different norms have been analyzed for POD wake. It is possible to note that for both Reynolds, the use of V-norm defines a package in the first modes of POD, and that they associated to the same wave number were dominant of the tonal noise. The same is not true for a U-norm, which despite having influence from the associated wave number, presents a shift in the first modes between low wave numbers and large wave numbers. And that use of the turbulent kinetic energy norm is just a combination of the other two maps. When computing the POD boundary layer using a U-norm, it is possible to identify the streaks present in the flow. Streaks are coherent and elongated structures close to the wall and carry a large portion of the flow energy, and as can be seen by the Fourier transfer of the first mode on the right, they are associated with low wave numbers. The maps of Fourier transform are highlighted using a U-norm for both Reynolds, and for each POD mode number, the amplitude is greater and more defined with U-norm instead of V-norm. The turbulent kinetic energy map is just a combination of the other two maps, and there is an increase in the maximum wave number of streaks for higher Reynolds. For the main conclusions, the mean profile of velocity for airfoils in regional log law does not coincide with the classical turbulent parameters of von Karman due to the adverse pressure gradient, curvature, and Reynolds number. The physical mechanism of ejectance and sweeps is evidenced in both scatter plots and PDFs. Two-dimensional structures with large energy on wake for Reynolds 200K and Reynolds 800K, responsible for total noise and wave number 7.3 and wave number 11, using V-norm on POD to identify the most energy modes on wake. For the POD boundary layer, use of U-norm to identify streaks present along the airfoil, associated with low wave numbers and increasing of the maximum wave number of streaks for higher Reynolds. I want to give my acknowledgements to Unicamp, CAPES, and the clusters Senapad, Santos Dumont, and Euler. Thank you.